Kia ora. In this video we're going to take a look at some rational functions and we're not going to go through all the possible techniques for integrating functions like these ones, but we will look at a few things that are likely to come up, in particular partial fractions, and we'll also practice some long division in case you haven't worked on that before. So the first example we're going to do is this one here, where we have the integral of a rational function. Now a rational function just means basically a fraction of polynomials. So here we've got a rational function, and the interesting thing about it is that the degree, or the highest power, is bigger on the numerator than on the denominator. So it's degree 5 polynomial on top and a degree 3 polynomial underneath. So our first thing we realize is because the numerator degree is higher, then before we can really make any progress on this, what we want to do is to use long division to turn this into something plus a fraction that's not of this form. So what we'll do is we'll jump into another page and just do that separately so we can sort of keep our main integral working tightly. So what do we have? We've got x to the 5 plus x minus 1 all over x cubed plus 1. So what we want to do is we want to do long division on this fraction to turn it into a polynomial plus a rational function where the degree of the numerator is smaller than the denominator. So we'll do it, set it up as a division problem. So we're going to be dividing by x cubed plus 1. And what I like to do is kind of lay it out so that we've got sort of 1 square. That's why I'm using the grid paper today. 1 square per power. So x to the 5, there's no x to the 4s, no x cubes, no x squareds. There is an x and there is a negative 1. This will kind of help us keep it into columns. So the question we ask ourselves is, what do I have to multiply x cubed plus 1 by so that the highest power term is x to the 5? And the answer is x squared. If I multiply it through by x squared, notice how I'm putting it in the square column down there, then what I'll get is x to the 5. So I'm multiplying x cubed plus 1 times x squared, and then we're plus x squared. So I'll put the x squared in the x squared column. Okay, next step of long division is to subtract off. So the x to the 5's cancel off, and what I get here is a negative x squared plus x minus 1. Now, I can't multiply x cubed plus 1 by anything to get the highest power equal to that expression, so that is going to be my remainder. So what this means, if we go back to our fraction, is we're saying that the thing on top, x squared, is going to be our standalone piece. So it's going to be x squared plus whatever my remainder was, that's this piece here, negative x squared plus x minus 1 divided by that denominator. So that's kind of how long division works. So we can go back to our integral and we can turn it into an integral of 2 pieces like that one there. All right, so let's have a look. So that equals the integral of x squared plus, now I've forgotten what it was already, let's just scroll back again, negative x squared plus x minus 1. All over x cubed plus 1 dx. All right, now we've got our rational function piece into the right form. We know how to deal with the x squared, that's just going to be an x cubed on 3, but I'll just leave it intact for now. Now, before we attack the next piece, we have to think about whether or not this fraction here can be factorized. Because when we're taking a rational function, the first thing we want to do is make sure that the denominator is as factorized as it can be. Now you might be thinking, oh my goodness, it's a cubic, I don't know how to factorize cubics. But the first thing you maybe want to think about when you're thinking of factorizing is there any number I can stick in, obviously, that will give me a 0? And if I just think about this for a second, if I stick in x equals negative 1, then that will give me a 0 on the bottom, which means there's one factor already. So x equals negative 1 makes denominator 0. So that means that x plus 1 is a factor. Okay, so that's nice. We know that x plus 1 has got to be a factor. There's a theorem that tells us that's the case. So what we can do is, again, go back to our long division and figure out what the other piece is. So maybe if you can eyeball it, you can figure it out for yourself. But I'm just going to practice my long division and do that again. So let's just skip back to our long division page. So now we've got x cubed plus 1. X squared, x is plus 1, and we're going to divide it by x plus 1. So first question is, what do I multiply x plus 1 by so that the leading term is x cubed? And the answer is x squared. And x squared times x plus 1 is going to give me x cubed plus x squared. Then I subtract that line off, which gives me a negative x squared. And then I bring down the plus 1 like this. Okay, now what do I multiply x plus 1 by to give the leading term of now negative x squared? It's like we're not working with x cubed plus 1 anymore. Now we're working with negative x squared plus 1. And the answer here is I multiply it by negative x. Okay, so multiplying that by negative x, I'll get negative x squared. And I'll get minus x. Okay, and we subtract that off, and we will get, subtracting negative x is going to be positive x, and we'll bring down that plus 1 again. And as expected, x plus 1 is exactly 1 times x plus 1, so this factorizes properly, which means that x cubed plus 1 is equal to x plus 1 times x squared minus x plus 1. Okay, so that, and then what about the x squared minus x plus 1? Can that be factorized? No, it can't, because if I look at the discriminant, that is b squared minus 4ac, if you like, from the quadratic formula, that will give me, just quadratic formula to tell me that x is, the solution to that piece on the right would be x is negative b, so negative 1 plus or minus square root of b squared minus 4ac. And that's going to be the square root of a negative number, and so that means that we're not going to factorize. So we can't factorize that any further, and so x squared minus x plus 1 is what we call an irreducible quadratic, because it can't be factorized. Okay, let's go back to our top page and put that in and see what happens. So that equals the integral of x squared plus negative x squared plus x minus 1 over x plus 1 x squared minus x plus 1. All right, dx. Now, at this point in time, things could get a little bit messy, and we might have to go and use partial fractions. But for this particular problem, you might notice that the denominator term, this one here, is just the negative of our numerator. So because this is a sort of a slightly contrived problem, that those two pieces cancel out, just leaving behind the negative sign. So that is just going to equal the integral of x squared plus negative 1, make it a minus here now just for tidiness, over x plus 1 dx, and now those are both pieces we can integrate. So it's going to be x cubed over 3 minus the log of the absolute value of x plus 1 plus a constant. Okay, so we'll do partial fractions in a separate problem because it just gets a little bit messy. So we'll start on a new one, and this time we'll look at what happens if we have to use partial fractions. So for our next example, we're going to do the integral from 0 to 1 of x squared plus x plus 1 divided by x plus 1 squared times x plus 2 dx. Okay, so first off, the degree of the denominator, that's the highest power of x, is going to be x cubed. If we expanded all that out, we'd get an x cubed term, and the degree of the numerator is equal to 2, which is smaller than the degree of the denominator, so there's no long division required to be done up front. Right, so what we're going to do is we're going to use partial fractions to turn this into the right kind of form. So again, I'm going to do this on a separate page just to keep my main working tidy. So just copy that, jump to a new page, paste it here, and according to partial fraction decomposition, we have a squared term on the bottom, a linear squared term, an x plus 1 term that's been squared, and so the form of the partial fraction decomposition is going to look a bit like this. A, some unknown constant a, over x plus 1 squared, plus some other constant b, over x plus 1, plus some other constant c, over the other piece, x plus 2. Okay, so remember when you've got a power, like a squared here, we have to introduce a term for every exponent. So I introduced a squared one, and I introduced a to the power of 1 term. The next step is to multiply out by the denominator on the left-hand side. So it's multiplying through by basically x plus 1 squared times x plus 2. And what that gives me is, well, obviously on the left it just goes away. X squared plus x plus 1 is equal to a. Now, the x plus 1 squareds will cancel, so it'll be a times the other piece, x plus 2, plus b times, or one of the x plus 1 squareds will cancel here, x plus 1 times x plus 2. And then for the c, well, the x plus 2 is going to cancel, and we'll be left with x plus 1 squared. Now our job is to find out what a, b, and c have to be. There are two main ways of going about this. Probably the most conceptually straightforward is just to expand out the right-hand side and match the coefficients to the powers of x on the left-hand side. So what do I mean by that? Well, if you look at the left-hand side, the coefficient of x squared is just 1. So that means the coefficient of x squared is 1. On the right-hand side, what's the coefficient of x squared? Well, there's going to be a b, because there'll be an x squared when those two things get mashed together. And there'll also be a c, because there'll be an x squared from expanding that x plus 1 squared there. So if we're looking at the terms, there's going to be, there'll be a b times x squared, and there'll also be let's leave them lined up, b, and there'll also be a c. If I look at the linear terms, the x terms, again on the left-hand side, the coefficient is 1. Well, I'm going to have an a from my first piece, an a times x. Then there's going to be in the second piece, well, if I expand that quadratic out, there'll be 3 x's, and there's a b on that. So it's going to be plus 3b. That's just from expanding this quadratic out. So the x terms are going to be from this one and this one. So there's 3 of them, and there's a b out the front. So that's where that comes from. Notice I've kept the a's and b's in a column, and then linear x terms, when I expand out this square here, there'll be 2x in it, and so there's going to be 2c as my coefficient of x. Let's try this again. It should be a there, plus 3b, plus 2c, just keeping it nice and lined up. You'll see why in a second. And if I want to look at the constant terms, on the left-hand side there's a 1, and then on the right-hand side there is a 2a. There is a, when I multiply the quadratic, the constant is going to be a 2, so there's a 2b as well. And when I multiply out x plus 1 squared, the constant will be 1, and so there is a c. And I then want to go and find a, b, and c. So if I want to do this, then basically what I'd be doing is setting up an augmented matrix and doing it by Gaussian elimination. So it'd be something like this. I'm not going to go right through it because I'll show you a slightly more straightforward way in a second. But I'd be setting up this problem here. Here's my augmented matrix, 1, 1, 1, and I can use that to solve for a, b, and c. That's method number 1, but I'll show you an alternative as well because it can be a bit easier to do it this way. It'll still give you the same answer, so either way is fine. The other option is to just substitute in some numbers for x. Because every time you put in x equals something, that will give you a valid equation. So for example, I'll start with x equals -1. Why is that? Because if I put an x equals -1, this term will be 0, this term will be 0, and we'll only have the a term left over. So on my left-hand side, when x equals -1, I'll get -1 squared, which is 1, plus x, which takes me down to 0, plus 1 again, and so I'll get the equation on the left, I'll get 1. Then if I look at the right-hand side, when x equals -1, -1 plus 2 is +1, so there'll be an a, and then these terms are both 0. So this tells me directly that a just equals 1. My next choice would be, for a similar reason, I can put in x equals -2. So let's just tidy up the working slightly. So this is x equals -1, gave me that equation. If I stick in x equals -2, then let's look at what terms are going to be cleared out by that. If x equals -2, this piece is going to be 0, this piece is going to be 0, and I'll only have the c term involved. So let's start with the left-hand side. If x is -2, -2 squared is +4, plus -2 is +2, plus 1 is going to give me 3. On the left and on the right, the a is gone, because that's 0. This is 0 here, so the b term is gone, so all I've got is the c. -2 plus 1 is -1. Square that, I get +1, and so that's just going to be 1c, or just c by itself. So see how this is getting me more directly to these numbers rather than having to necessarily set up a full matrix system to solve. Now we don't have any more magic numbers to put in because there's no other number that's going to make factors go to disappear, but maybe we could use any number we like, but x equals 0 seems like a smart choice because it should hopefully result in something fairly simple. So if I stick in x equals 0, on the left-hand side, that's 0 squared plus 0 plus 1 is just 1. On the right-hand side, we'll have 2a plus, let's see, 0 plus 1 times 0 plus 2 is just 2, so it's going to be 2b, and then plus 0 plus 1 is just 1, so it's plus c. And we can use that last equation to get b fairly directly, so that will tell me that b, just rearranging this, I'll do it in one hit, 1 minus 2a minus c, all divided by 2, which is going to be equal to, I'm just going to do it slowly so I don't make any mistakes, 1 minus 2 minus 3, which sounds a lot like -4, all divided by 2, which just equals -2. So what does that mean? So b is -2, a is 1, and c is 3. So that means if I go back to this expression here, I can put those values in. So just fence off the space. So that equals, so I said a was 1 over x plus 1 squared. I said b was -2, so minus 2 over x plus 1. And then I said c was 3, so plus 3 over x plus 2. So I've split up this fraction now, so I'm now going to go and take this and put it back with my problem. It's quite good to do the working for these pieces separately from your main sort of line of working, because otherwise things can just get a bit muddled up. So let's just paste that in here. So that equals the integral from 0 to 1 of that thing there, dx. Now with a bit of luck, once we've done our partial fractions, then you can use fairly standard techniques to do each piece separately. Sometimes there'll be a trig term involved, sometimes there'll be logs, sometimes there'll be just powers. So let's just go through these one by one. So it's integral of, so we're just going to be ambitious and put the bracket, hopefully we can do them all. But let's see, 1 over x plus 1 squared, that is just a power. So I could do a substitution, I'm not going to because it's kind of simple enough that you don't need to do this. U equals x plus 1, then it's just going to be an integral of 1 over u squared, which is going to be -1 over u. So that piece there, and again I'll let you go back to previous week's working if you want to remember how this works, is just going to be negative 1 over x plus 1. And if you want, you can differentiate that just to confirm that that is the case. Okay, what about the 2 over x plus 1? Well, that's just going to be a natural log. Again, I could do u equals x plus 1 substitution, and I'll find out that's just going to be 2 times the natural log of the absolute value of x plus 1. And likewise, this one is a similar piece. And again, you can test them by differentiating if you like. Derivative log of x plus 1 is 1 over x plus 1, and by chain rule you multiply that by 1, so those are all going to work. Okay, we're almost there. So all we have to do now is just be a little bit careful and substitute in those values, because we are doing a definite integral. So we'll do the 1 pieces first. So it's going to be negative a half. Okay, that's x plus 1, negative 1 over 2, minus 2 log 2, plus 3 log 3, because the absolute values can go away because we know those numbers are positive, minus, now we're going to put zeros in, negative 1, yep, that's right, minus 2 log 1, that's just 0, plus 3 log 2. And it's probably a little bit nicer if we just clean this up slightly, because there are some matching pieces. In terms of the constants, there's a plus 1 on the right there. A negative 1 is just a plus 1, and there's a negative a half. So overall that gives me 1/2. Log 2 terms, there's negative 2 of them here, and there's negative 3 of them there. So overall there are negative 5 of them. And then log 3's, there's just that plus 3 log 3. Cool, all right, I think we'll call it quits there. So just basically the key with these things is just to be slow, methodical, and practice plenty so that you don't have to think too hard about what you're doing. That each step should hopefully become relatively automatic as you practice. All right, we'll see you next time.